Hello, everyone, and welcome to another episode of the GC 100 podcast. I'm your instructor and host, Dr. VG. All right, today we're going to be focusing our attention on the Earth, Sun, and seasons. Specifically, click, there we go. We'll kind of begin our journey here thinking about the place and shape of Earth within the universe, really, in our solar system, and then kind of focusing more on rotation and revolution. Finally, then it all kind of leads up to our understanding of seasons and the geometry of Earth and the sun together. So, where do we begin? Well, might as well go way back in time here and think about the Big Bang Theory. It all began approximately 14 billion years ago. That's kind of a long time, where all matter emerged from a dense, high temperature swirling mass that led to the creation of a galaxy. And then here, our galaxy being the Milky Way. And so our galaxy contains 400 billion stars. That is like that number I'm always in awe of. It's just so huge. There's 400 billion suns effectively just in the Milky Way. And as far as we know, there's over 50 billion galaxies. So just kind of try to wrap your head around that. I never really can. But anyways, let's kind of narrow our focus here and think a little bit about the solar system. So our sun, which is a star, is at the center of our solar system, and we have 8 official planets where Earth is the perfect distance away from the sun to support Earth. But unlike Macho Man Randy Savage, who is too hot to handle and too cold to hold, our Earth is this perfect distance, so we're not too hot or too cold. So it's pretty darn nice. A little bit more about Earth geometry here. We are almost a sphere. In fact, we're what is known as an oblate spheroid, which means that the poles here are a little bit compressed and it's bulging at the equator. So it's effectively like flatter near the poles and bulging near the equator, where then if we were going to measure the circumference around the equator is larger than the poles, as you can kind of see in this picture. So we're not quite a perfect sphere. Here, kind of like really setting us up for the next handful of lecture topics. Really, it all kind of interrelates and comes back to some of these really kind of foundational properties and principles associated with Earth-Sun geometry. And so the angle at which sun's radiation strikes Earth's surface has a huge influence on the amount of energy in the form of radiation received by Earth at certain locations over periods of time. And so effectively latitude really kind of controlling these angles, and we'll talk a little bit more about tilt and rotation and revolution, but latitude has a major driving influence on total energy budget for a certain particular location, like the pole versus the equator. Effectively, and then kind of generalized here, higher latitude, so near the North Pole or near the South Pole, have lower sun angles. The sun is coming in, and because we're tilted, the angle of incidence where the sun strikes Earth's surface is much lower. So it's actually effectively like closer to the horizon when it's actually above the horizon near the poles. Whereas near the equator, the sun in the middle of the day, every single day, is almost perfectly overhead. And we'll learn a little bit more about that as we move on. So low latitude locations have higher sun angles, specifically latitudes near the equator have nearly 90 degrees, or on a couple days a year, they have exactly 90-degree sun angles in the middle of the day. So we're just kind of another representation here of what that looks like. So lower angles near the poles for you, if you put a stick figure and you're standing at the surface, what that looks like is that in the middle of the day, if you're at a northern latitude location, like near the Arctic or Antarctic Circle, then the angle, the sun is actually only like 20, 30, 40, or in this example, 45 degrees above the horizon. And so, and then if you are at the equator here, the sun's effectively overhead directly in the middle of the day, where the sun is directly coming down and striking Earth's surface at a 90-degree angle. If you took a flashlight and you flash it directly straight down on your desk or on the surface, you'll see that that flashlight makes this like kind of perfect concentric circle of radiation. Where, however, if you take that flashlight and you tilt it here kind of at a 45-degree angle, you're going to see that same amount of energy coming from the flashlight in the form of radiation. Now it's going to spread across your desk over a greater surface area. So what that means is you have the same energy here and here up in the sky as the sun's energy comes to Earth's atmosphere and into the surface. But when it finally strikes the ground, that angle at which it strikes the ground has so much importance that in this case, if you spread that energy out, any single point then on Earth's surface is receiving less energy with these lower angles. So the lower and lower it gets, the more that energy is spread out over Earth's surface, meaning you could spread the same amount of energy out over twice the surface area near the poles because it's a low angle getting spread far, where when it's highly concentrated near the equator and directly overhead, you're concentrating that same amount of energy in a smaller space on Earth's surface. Okay, so that take home for that is higher angles, known as sun altitude. Higher sun altitude angles near the equator concentrate the energy in a smaller surface area, where the lower sun altitude angles near the poles spread that energy out over a larger surface area. We're going to return to this term known as the subsolar point a few times this lecture, but here to define it, the subsolar point is the point on Earth's surface where the sun strikes exactly at a 90-degree angle, so that at any given on any given day, there's only one point, 1 degree of latitude, or one location latitude specifically, where the sun reaches 90 degrees above the sky. And so we'll think about rotation and revolution and how that migrates over time. But effectively and directly here, the subsolar point is the point on Earth's surface where the sun's altitude, the angle, is exactly 90 degrees, and the energy, the radiation, is striking most directly at that location on Earth's surface. Okay, so now let's explore revolution and rotation. We have a counterclockwise rotation and revolution. So we'll get to rotation. So here, counterclockwise revolution around the sun. Our Earth is revolving in a counterclockwise manner here, like you can see. So how long does it take for the Earth to complete one full revolution? How many days? Well, if you said 365, you'd be almost correct. In fact, it's exactly 365.24 days, and that is why we have a leap year once every 4 years. All right, so in terms of now kind of like going back out into space, if we were looking at the sun and all the planets from afar, all of our planets line up, or most of all of our planets line up for what is known as the plane of the ecliptic. It's the plane lining up all of the planets' revolutions, orbits around the sun, where you can see most of the planets have a pretty similar angle where the sun's here and we're all revolving kind of in that same or approximately the same plane, with the exception of Mercury. Our elliptical path, the revolution, is not perfectly circle. In fact, it is an elliptical path. It's an ellipse. So actually, at some point in the year, every year, our Earth is closer to the sun, and at a different point, the aphelion here, it's further away. So the perihelion is the closest point, and in fact, that's in our winter. So we're closest to the sun during the winter, and we'll talk more about why that angle of radiation matters here moving forward in terms of why it's colder on Earth's surface in the northern hemisphere in the winter. But And for this here, the perihelion is the closest point documented or kind of depicted here. And then this elliptical path, we move a half a year later, we're at the farthest point away from the sun. So in fact, in the middle of our summer, approximately here in the northern hemisphere, we're the farthest away from the sun at the aphelion. So Earth is tilted effectively relative to the sun, at least in the context of where our geographic north and south poles, which is the points of our rotation. And so we're rotating, spinning on that axis, and that axis is spinning not perpendicular to the sun, but the Earth is now tilted at about 23.5 degrees relative to perpendicular. So if the sun was over here and this is perpendicular, our Earth is tilted at 23.5 degrees, and that tilt remains constant. For our lifetimes anyways, that tilt is always at 23, actually 0.45, but approximately 23.5 degrees. We're now rotating also counterclockwise. So we're both revolving around the sun counterclockwise, and we're also spinning or rotating counterclockwise. And we effectively move from west to east as viewed from the North Pole. And so if you were floating above the North Pole, looking down on the North Pole, we're rotating from west to east as viewed from that location. And it takes exactly 24 hours to complete one full rotation. Then now we're gonna start kind of exploring more what does it look like? Where is the circle of illumination? There's always half of the Earth that's dark and half of the Earth that's light. The side of the Earth that is facing the sun is within the circle of illumination, and the opposite side then is in the dark. So there's always a half of the Earth in dark, and that is the boundary here. This yellow line is the boundary between day and night. And then I just kind of added another line to kind of show that axis degree. And so here's the tilt at 23.5 degrees. Here's the North Pole and the South Pole, and it's 23.5 degrees relative to that perpendicular angle to the sun. So a little bit about rotation and time. How many time zones on Earth are there? Well, there's 24. Every time zone is 1 hour, and we go from 1, 2, 3, since it takes 24 hours to make one complete rotation. There are 24 time zones. And so if you took 360 divided by 24, you could estimate or figure out how many degrees of longitude there are per time zone. And in fact, that is 15 degrees. So every singular time zone occupies 15 degrees of longitude. Remember, longitude are lines that run north and south, and then effectively we're using it to determine our location east or west of that prime meridian. But why don't the time zones perfectly line up? If they perfectly lined up with those 15-degree marks, all of these color shadings would be perfectly aligned with the lines of longitude. But why don't they perfectly line up? Well, politics, of course. And so different countries and different locations, and even for us, different counties within a state deciding to be effectively in Central or Eastern time, all depending on kind of commerce and politics, if you will. So kind of going back and then bringing it to the present here, the prime meridian again is the 0-degree line of longitude, and that then is the standard for our time zone system. Where at 180 degrees, the exact opposite side of the Earth as the prime meridian, is what is known as the international date line, which is the 180-degree meridian, and that marks the start and end of each global day. Effectively, for time zones, then, we are centering at the prime meridian at zero, and time in terms of time zones gets 1 hour earlier and earlier and earlier as you move west of the prime meridian. And then as you move east of the prime meridian, or just east in general, every time zone, then it gets a little later and later and later. So it's always later than us in this portion of Europe, and then it's always earlier for us here in the Great Lakes. If you're calling your family out in Washington State or in the West Coast where my family lives, it's 3 hours earlier. All right, so now let's kind of connect some of what we've been learning here and think and apply it to why we have seasons. So why do we have seasons? Well, it's a combination of both the tilt and then our revolution. I really like both of these images in terms of their simplicity as well as how they're lining up with these geographic grids and features. Here, kind of specifically, again, we're revolving counterclockwise. Our Earth is tilted at 23.5 degrees relative to perpendicular from the sun here, and that tilt remains constant. So as our sun, or sorry, as our Earth moves from one side of the sun rotating to the other, it's maintaining that tilt, and the tilt and the tilt always stays the same, and the tilt coming back. And so here the tilt, so that means literally at some point in the year, the northern hemisphere, where we are, is pointed toward the sun, and that the exact opposite time of year, the Earth is pointed away from the sun. That then, kind of going back to earlier portions of the lecture topic, thinking about sun angles and radiation, has a big influence on where the most energy is received on Earth. And so here during our summer solstice, I'll define that in a few slides. Here in the middle of summer, so to speak, at our summer solstice, the subsolar point specifically, where the angle of solar radiation is striking our surface directly at a 90-degree angle, is furthest north. In fact, it's directly over the Tropic of Cancer here, and so further up 23.5 degrees north of the equator. And so most of the energy on Earth is being received here north of the equator in the middle of our summer, whereas on the opposite time of year, approximately in the winter or the winter solstice, then the subsolar point is located directly above the Tropic of Capricorn. So most of the sun's energy here being concentrated in the southern hemisphere during the winter, or at least the winter solstice period. I do recommend a short click here and watch this short YouTube video to kind of help support this understanding of Earth-Sun geometry and radiation. A couple more details and slides focusing on tilt and rotation. So specifically, our tilt is 23.45, or rounded up to 23.5, from the plane of that ecliptic, going back to the plane and the sun in the middle and the Earth's revolution around the sun. That angle remaining constant. So our tilt of the Earth relative to the sun never changes. We revolve around the sun, and that tilt at 23.5 degrees is always the same. Just kind of refreshing, kind of different figures here to help reinforce that. Within this, we can think about Earth's angle, or sorry, the sun altitude angle, which is relative to the horizon. So that's really, and on the next slide, I'll highlight that more. It's often what we think about as we're humans, we're on Earth's surface, we think about where is the sun in the sky, and so the sun altitude angle is relative to the horizon. Here, the declination angle is the angle of the sun relative to the equator. And so in the middle of the summer, at the summer solstice, when the sun is directly above the Tropic of Cancer, it is 23.5 degrees north of the equator. And so here the declination angle is the angle between the rays of the sun and the plane of Earth's equator. So it's this angle right here. You can see then in this lower figure effectively what that means for where is the sun relative to Earth's surface. In the middle of our summer in the northern hemisphere, the declination is 23.45 degrees north, and so it's striking our surface here 23.5 degrees approximately north of the equator. On each of the equinoxes, which I'll define here in a little bit, the equinox being March and September 21st approximately, the sun is directly above the equator, and so the declination is actually zero. There is 0 degrees between where the sun is and the equator, and then in the southern hemisphere during our winter, sun is striking Earth's surface, the subsolar point here south of the equator, or negative 23.45 degrees relative to the equator. So that all focused on declination angle, and then here the concept of a celestial dome, or really the angle of the sun relative to the horizon. And so that's how we as humans are observing the sun. We have approximately 24 hours, including a period of day and night, and we'll think a little bit more critically here moving forward in the course about length of day, where we have longer days in our northern hemisphere summer and shorter days in our northern hemisphere winter. But here kind of showing the arc, this path of the sun relative to a human or a stick figure and the horizon. And so that path the sun takes in the sky. Effectively, in our northern hemisphere summer, the sun, that arc, the celestial dome, the sun is up longer, so the duration of radiation received by Earth during the northern hemisphere is quite a bit longer, and that angle, the highest angle achieved, is in fact much higher during our summer than compared to our winter. So another image depicting this same property. And then, as we've been talking about, and then here for the specific definition, the sun altitude is the angle of the sun above the horizon. So if you're the observer, you can directly measure the angle of the sun relative to the horizon. And so the higher the angle, the more direct the radiation received, the lower the angle, the less direct, and then that same radiation again being spread out over a greater area at these lower sun angles. Something I always kind of appreciate here in Marquette, Michigan is in the winter, even when the sun is out and it's not cloudy or snowing or some other form of precipitation, the sun is only like about 20 some low 20 degrees above the horizon. It only ever gets like that far above the horizon, where that energy then is spread out over a much greater surface area in the middle of the day, compared to our summer, when in the summer our sun angle is kind of not quite 70, it's almost 70 degrees in the middle of our summer. So this 73 showing maybe somewhere down near Chicago, for example. But again, pretty darn high, but that difference between low 20s and 70 is quite substantial in terms of how that energy from the sun is concentrated on Earth's surface. The term solar noon then referring to literally the time at which the sun transits the highest point in the sky. So it's the time when the sun is highest in the sky. And so the morning comes up and the sun's going effectively in terms of the observer, the sun is going up in our sky, and the point at which it reaches the highest elevation or the highest angle is solar noon. I encourage you, for kind of like all of these last concepts, thinking about the relative position of the sun, the subsolar point, length of day, where the subsolar point is at different points in the year. These series of labs from the University of Nebraska-Lincoln are really, really useful, kind of to help visualize and conceptualize these Earth-Sun geometry relationships. I particularly like these two. There's many labs listed on their homepage, and then here you can directly click to view the basic coordinates and seasons lab. Here's a hyperlink, and then here the motions of the sun lab directly. So these are two of the simulator labs you can kind of click and play around with to better familiarize yourself with Earth-Sun geometry. Okay, so now to bring it all together. And so we're going to emphasize subsolar point here and moving forward in the class, as that has a huge influence on many things, including climate and biomes and many other properties as we explore all aspects of all four of Earth's spheres in this course. So here, thinking about the solstice or solstices as well as equinox on the next slide. So our summer solstice, which is on approximately June 21st. Please be aware that for each solstice and each equinox, that specific time, the subsolar point is directly above the Tropic of Cancer for our summer solstice, is right around June 21st. In fact, on any given year, it could be on June 20th, 21st, or 22nd. So there's a specific time, literally, and that time could be kind of towards the end of June 20th or on June 21st or June 22nd. So typically on any given year, and for this course and these slides, we're really going to kind of focus on the 21st dates. But again, just remember that they can occur over a 3-day range. So here, showing the subsolar point for the summer solstice is located directly above the Tropic of Cancer, meaning sun's radiation is striking Earth's surface at a 90-degree angle directly above the Tropic of Cancer, meaning most of the energy received from the sun is being concentrated in the northern hemisphere in the summer. During our winter, on the winter solstice on December 21st, it's the opposite then. As we revolve around the sun and our tilt remains constant, then the subsolar point is directly above the Tropic of Capricorn, which is 23.5 degrees south of the equator. For our equinoxes, 2 times every single year, on March 21st and on September 21st, sun's rays are striking Earth's surface directly at the equator. And so the sun altitude angle is 90 degrees at the equator on March 21st and on September 21st, the spring and fall equinoxes. With that, we've brought ourselves to the end of this lecture topic, and as promised, we'll kind of continue to explore Earth-Sun geometry, thinking about electromagnetic radiation, and then temperature, atmosphere, biomes, and climates. It's all interrelated, and I'm excited to get into all of that with you. So with that, Dr. VG is signing off.